Okay, I'm going to talk about random variables. Now we have two types: discrete random variables and continuous. An example of discrete might be something like this, where if this is f of x, x only has a probability of occurring at these discrete values, as opposed to a continuous random variable, where x can take on any value in an interval. Or sometimes you can have it go to infinity on both sides. So x can take on, it's not confined to discrete values. So we denote it with f of x. So in discrete random variables, we call f of x the probability mass function. In continuous random variables, we call it the probability density function. Now, a requirement for both of these functions is that for any f of x, it must be greater than or equal to 0 and less than or equal to 1. Another requirement is that if you sum f of x for all x, it should equal to 1. And that applies for continuous random variables as well, except you have to take the integral. So this is equal to 1. There's something called a mean, and essentially it's the expected value of x, so the value that we expect x to have. Now, before this, I'll explain what expected value is. So expected value we denote as e of any function of x. So this would mean take the sum for each x of h of x multiplied by the probability of x. So for continuous, this would give us from negative infinity to infinity h of x times f of x dx. So this gives us the expected value. Now the mean is essentially the expected value of x. So x times f of x for all x, and for continuous random variables it would be x f of x dx. Now there's also something called variance, which we sometimes denote as v of x, and it's also denoted with a sigma squared. The variance is the expected value. I'll write that down too. It's the expected value of x minus mu squared. So we just plug this in to this formula, and we get x minus mu squared times f of x for all x, and for the continuous we would get x minus mu squared f of x dx, integrated from negative infinity to infinity. Now I would like to write down an important formula that has to do with variance. So variance, we said, was the expected value of x minus mu squared. Now this is also equal to the expected value of x squared minus mu squared, or if it's easier for you to remember, you can think of it as expected value of x squared minus expected value of x quantity squared, because mu is equal to the expected value of x. Oh, I forgot to write that down. The mean, as well as being written as the expected value of x, it's also written as mu. So don't forget that mu is equal to the expected value of x. Now this formula makes it easier for us to find the variance in some situations. There's also something called standard deviation. It's denoted with a sigma, and sigma squared was variance. This is essentially the square root of variance. So it's the square root of v of x. So for discrete, that would be the square root of x minus mu squared f of x. And for continuous, that would be square root of the integral now you could, instead of this you could use the formula that I used up there. It makes it easier in some situations. But once you found variance, just take the square root. That's essentially how you find the standard deviation. Now, if we have f of x, there's a different way to write this. This is how I write it. X hat is equal to x. So essentially, an example would be f of 2 is equal to probability. That's how you read this. The probability that x is equal to 2. So x hat. In books, normally they write a capital X here. My capital X looks exactly like my regular x, so I just use an x hat to differentiate. It gets confusing when you use both of them at the same time. But remember that this x is equal to this x. It's the same thing. So this is the PMF or PDF. Now there's also something called a CDF, which is the cumulative distribution function. And it's essentially, we denote it with a big F, capital F of x. And it's essentially, instead of taking the value exactly at x, it's all values less than x. Less than or equal to, actually. So you're taking, if you have a graph, you're taking everything below that. So you're taking the area of under the graph for continuous random variables, and you're just taking the sum of everything below it for discrete random variables. So an example would be if you have 0.1, 0.3, 0.2, 0.4. So if you're taking the value, let's say this is x0, capital F of x0 would be 0.1 plus 0.3 plus 0.2. So everything below that value, you add it together, so that would give us 0.6. This is obviously different than f of x0. So this is just the probability that x is x0, so that would be 0.2. Now, in continuous random variables, you did essentially, if you want capital F of x0, you would take the area from here and below. So anything before this. Obviously, if the graph doesn't exist below this value here, then you just have to take this in the middle. So whatever, so let's call this 2. So from 2 to x0, integrate f of x dx. So that's the cumulative distribution function. Now, when we're talking about continuous random variables, the probability that capital X is less than X is the same thing as the probability that capital X is less than or equal to X. So here, equality, the exact value doesn't matter. It doesn't matter if you say less than or equal to, it doesn't matter, because when you integrated it, you put the number, that limit, you put it on top, so it doesn't really matter. This gives you the same value. Now, I think that's it.